Most of us don't give any thought to jellyfish, except as nuisances that can inflict painful stings and close beaches. But Dr. John Dabiri thinks about them all the time. To him, jellyfish are an inspiration.
We've been working on jellyfish now for 10 years or so, and are still just scratching the surface of all they have to teach us.
Dabiri is a professor and a researcher at the California Institute of Technology. He's won a collection of major awards, a citation from the president, and a MacArthur Genius Grant. Yet he's learning from a primitive creature that has no bones and no brains.
Well, I think nature is probably our most important teacher because of the number of years of evolution that it's undergone. In the case of the jellyfish, having such a simple system that has gone through periods of extinction and other maladies and still survived, I think it tells us that we have something to learn from them.
Surprisingly, when Dr. Dabiri was growing up in Ohio, he was more interested in machines than marine life.
I grew up always interested in mechanical devices. As a kid, I would take my toys apart to see how they worked, and when I went to college, I studied mechanical and aerospace engineering. And it wasn't until the end of my college career that I did a summer internship here at Caltech, and that was my first real exposure to biology. I expected that we'd work on, helicopter design, airplanes, something mechanical, something I was used to. And so, to be honest, I was disappointed when he said that the project would be related to biology, because my only understanding of biology was through a high school class, which, to be honest, wasn't the most stimulating for me.
But that's how he ended up in Mort Garib's laboratory. There, he discovered that even the simplest living things are exquisitely complex machines, with valuable lessons to teach researchers with patience and imagination.
Our approach is to look at biological systems from the perspective of an engineer, to see them as mechanisms and devices, and to try to learn from those animals new design strategies for new technologies.
In Garib's lab, they studied jellyfish in tanks, but found that to really understand them, they'd need to study them in their natural habitat. So, how do you study a squiggly little bit of gelatinous material deep in the ocean?
Well, the first challenge in studying jellyfish is that they're swimming in water that's essentially transparent. So our first task is to find a way to track the motion of the water. The way we do that in the ocean is by using lasers to illuminate the sediment that's floating in the water column. And then we use high definition cameras to track the sediment motion to infer the water motion. So illuminating the particles in the water is still one of the big technological challenges, because we're typically competing with the sun, which is obviously a very bright source. So right now, most of our research is done at night. The divers will scuba dive in the nighttime so that the laser sources don't have to compete with any background sources.
Dr. Dabiri's work at the Biological Propulsion Laboratory has gotten interest and funding from some surprising sources, like the U.S. Navy.
So our goal isn't to build a robotic jellyfish per se. It's really to understand what are the physics behind the efficient jellyfish motion and to apply that to the underwater vehicles. So in the case of the work we're doing for the Office of Naval Research, the end vehicle actually looks closer to a typical submarine. It's just that we've designed devices that can modify the flow that's created, the water currents that are created, in such a way that the water currents look like they were created by a jellyfish, even though they were created by this mechanical submarine.
Dr. Dabiri says one of the fun things about science is that you never know where your research may lead. Studying the swirls and eddies produced in the wake of swimming jellyfish inspired him to look at the flow of blood inside the human heart.
And what's happening, especially as the blood enters the heart after being oxygenated by the lungs, is that it creates what's called a vortex ring. This is essentially a donut-shaped swirling current of water, or of blood in this case, that's entering the left heart. And it's very similar to the water vortex rings that jellyfish create as they swim. And so those vortex rings will create a sound that you can hear audibly, and hopefully will provide a key diagnostic for understanding healthy function of the heart versus abnormal function.
But diagnosing heart problems is just one of the payoffs from learning how fluids and sea creatures move.
Now, in the process of studying biological systems, one thing that I've always observed, especially in underwater organisms like fish, is their ability to school, meaning that they swim in these coordinated patterns in the water. And it's been hypothesized for decades that this could have energetic advantages, meaning that a fish in one of these groups might be able to swim using less energy than if it was by itself. And the way that it would achieve this is by each fish interacting with the swirling water currents that its neighbor was creating.
If fishes in a school can operate more efficiently than fishes swimming alone, Dr. Dabiri wondered what would happen if you created a school of windmills. He says putting regular windmills like these close together wouldn't work very well.
The status quo for the horizontal axis wind turbines is that because after the wind passes through one of these turbines, it's so turbulent that the energy is essentially of low quality for neighboring turbines. The design strategy is to place them as far apart as possible. And so this also impacts the amount of land that's required in order to generate usable electricity.
But there's another kind of windmill where blades rotate around a vertical axis. It looks like a 30-foot high egg beater.
And so our question was whether we could use the fish school as an inspiration for the design of wind farms based on these vertical axis wind turbines. Initially, it was simply a computer model that predicted outstanding performance, and it was so compelling to us that we started a research wind farm here in northern Los Angeles County, where we've been able to demonstrate in the real world that this approach can be effective.
Dabiri has shown that his wind turbines can enhance each other's operation when they're placed close together.
Much like the fish using less energy in the school than it does swimming by itself.
Although each vertical windmill generates less energy than one of the giant propeller-driven generators, they can be packed together until they almost touch each other. They're quieter, far less visible, easier on wildlife, and most importantly, they can be located closer to cities where electricity is needed.
So we've done that calculation at our field site, and what's so striking about this result is the magnitude of the improvement. It can be up to a factor of 10 on a given plot of land in terms of the amount of energy that you could extract.
10 times more energy per acre, courtesy of a school of fish. New tools to diagnose heart disease and advanced designs for fast, efficient submarines thanks to a sea creature that predates the dinosaurs. Surviving for hundreds of millions of years means overcoming countless challenges, each victory a triumph of form and function. Dr. Dabiri believes that by looking closely at these ancient creatures, we'll find answers to big, modern challenges of our own in transportation, medicine, and energy. I'm Bob Hirschon for Surveillance, the Science